two senators from the same state will not happen over here. Okay? So this is choose 5 states out of 50. And then from each state, there are 2 senators, so we have 2 options to choose from. So this is how you set up. Okay, so that is, this is a huge number, and I calculated that, so that is 2118760 times this is 32. Divide by 75287520. So that gives you 0.90. So 90% of the time, yes, it just those 5 senators selected to form a committee. They are coming from all 5 different states. Okay, 90% of the time. All right, example 8. Selection of children. A class of children, there are 12 boys and 8 girls, in which 5 students are chosen to go to the board. Okay? The 5 students. I have to say that one at a time. One at a time. So in other words, the first child picked, that person goes to the board, and next, another person. Okay? So here we go. What is the probability that no boys are selected? No boys are selected. Why? Because just all the girls went to the board. Okay? So what is the probability that no boys are selected? Because only girls selected. Only girls selected. So let's compute. Only girls. So go to these girls. There are 8 of them. Okay? So there are 8. Oh, I'm sorry. Not 8, 12, 10. 10 of them. Okay. So 10. First, you have a choice of 10 girls, right? So 10. Next, you have a choice of 9 girls left. 8, 7, 6, only 5, okay? And what about the all possible outcomes over here? So all possible outcomes, that means boys or girls regardlessly. So that is 22 times 21, 20, 19, 18. You know what I mean? Okay? So once you compute that, that one is going to be 0.0096, almost 0. Okay? There are just more than half is boys, and you select 5 of them, and just no boys are selected. That means like almost certainly it's not going to happen that way. Almost. So this is very, very simple. I mean, it's 0.96%. So it's less than 1% of the time this will happen. Okay. The next one, what is the probability that the first 3 children selected are girls? We talk about just first 3. Okay, first 3 3 selected are girls. So what about the 4th? What about the 5th? It doesn't matter. Well, what we are thinking about here is only the first 3. So, ready to change this one to probability? Yes. Again, or what about the all possible outcomes? Yeah, that is, I'm sorry, not 22 children, so 22, 21, 20, 19, 18. Yeah, oftentimes to computing the figuring out the denominator is easier. Okay, all possible outcomes. First 3 selected are girls, so be careful. There are 10 girls, so 10, 9, 8. Those are girls. From the 4th child, the gender doesn't matter. Could be another girl, okay? But it doesn't matter. But the next one could be a boy, okay? So go. 3 children are picked, selected. So how many are left? So 22 minus 3 is 19. Is that right? So those are all the candidates for the 4th and the 5th. So the 4th is 19 and the 5th is 18. Okay? And then just we meet the requirement. First 3 selected are girls. So when you do this, you calculate this probability, the fraction. So what is that? That is okay. The first 3 selected. Oh, I didn't compute that. Okay, 720. 720 divided by 22, 21, and 20. So that is 0.0779. 0.0779. So let's see, 1, 2. So 7.79% of the time, yes, the first 3 selected are girls. Okay? Okay, just 2 more problems. Yes, then I will finish in 75 minutes. Okay. Example 9, dice. A die is rolled 3 times. What is the probability that you observe 3 different numbers? Okay, so you roll a die 3 times. 3 times, and then you see just different numbers. Okay, you see all different numbers. So, what are the all possible outcomes? Okay, each time you roll a die, so how many different cases are there? So first roll, 6 different cases, right? Second roll, again, 6 different cases. And the third roll, again, 6 different cases. So the denominator is going to be all 6, 6, 6. On the other hand, each time you are going to see different numbers. So let's say the first case, yeah, or just any of those 6 numbers possible. The second time, it has to be different from the first number. So let's say first number was 5, and then other than 5. Okay, so 5. The third row, again, different from the 2 previous cases. So there are 4 possible outcomes there. Okay, so that is 6, 5, 4. So what is that? 6 cancels. Okay, 6 cancels. that gives you 20 over, 36. That gives you 5 over 9. That is a little more than 50%. So 5 divided by 9. That is 0.555. So 55.5% or 6% of the time, you are going to see just all different numbers. Last example, coin tosses. Yes, we cannot avoid any kind of coin toss problem here. Okay, coin tosses. A coin is tossed 10 times. Yes, 10 times. Okay. Before I go further, in the previous chapter, we did coin toss problems, right? Okay, just try to recall what we learned over there. A, what is the probability of obtaining exactly 4 heads? Yes, when you toss a coin 10 times, a minimum of 0 head or maximum of 10 heads, right? Okay, anything in between. So this time we are going to compute the probability that exactly 4 heads occurs. And of course, if there are 4 heads, that means there are 6 tails. That is just automatic, okay? So you don't have to think about it. So what is the probability? So let's recall here. Let's recall. When you toss a coin 10 times, how many sequences are possible? Number of all possible sequences. Each toss will give you 2 different outcomes, right? So that's why 2, 2, 2. You multiply 2 times, that gives you 2 to the 10th, which is 1024 sequences. Out of that, exactly 4 heads. So exactly 4 heads. That is combination 10 choose 4. This is what we learned in the previous chapter, and you had a test on that material. So you learned this and you learned that. Are they related to, do we need this to set up this probability? Absolutely. Okay? All possible outcomes, that goes to the denominator. So 2 to the 10th goes to the denominator. And this 10 combination, 10 choose 4 go to the numerator. Okay? So what is it? That is 210 over 1024. Okay, that is 0.2051. So roughly 20.5% of the time, yes, you are going to see exactly 4 heads. Next thing is, what is the probability of having the first and the last tosses are the same? Okay? So it doesn't matter how many heads or how many tails, that's not an issue. Over here is the first and the last 2 tosses. So for example, the first toss and the last toss, or the 10th toss, they are going to have the same outcome. Okay, so let's do. First toss, how many outcomes are possible? 2. Second toss, okay, here, second toss, 2. Third, 2, 2, 2, 2, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. When you arrive the last toss, whatever happens in the first toss, it has to match that one, right? You are going to copy whatever you had over here. Therefore, the possible outcomes over here is going to be you compute just one over here. You know what I mean? Because the last one has to be the same as the first one. So when you set up the probability that, so first and the last toss, or tosses, have the same outcome. So how many 2's are here? 9 of them, 2 to the 9th power, and the denominator is 2 to the 10th power. Oops, interesting case. You don't have to calculate what that is. That is, you have 9 copies of 2, and then you have 10 copies of 2's. So what is that? Once you reduce, it's going to be 1/2. So 50% of the time, you are going to see the same outcome in the first toss and the last toss. We calculated this. On the other hand, do you feel like, well, you worked too hard for the very simple idea? Guess what? There are only 2 outcomes for each toss. So the last one is going to be either the same or different. You know what I mean? The same or different. So that is a 50-50 chance. You can think that way. Then you can go to just 1/2 directly. Okay. Well, I want to do just one practice problem on page 81. That is about the lottery. So it doesn't matter whether this is Florida or any other states, okay? So you are going to play some state lottery over here. State lottery, and it consists of 6 numbers. 6 numbers from 1 through 53, and order doesn't matter. Okay? What is the probability to win the lottery? What is the probability? So let's use the word jackpot. Okay? Hit the jackpot here. Only one ticket will win. Okay? Only one ticket will win. So that is, do not think about how many people buy the ticket. But that is irrelevant over here. What is the probability that you hit the jackpot? That is, only one will hit the jackpot. Okay? Only one outcome will matching the state, the winning numbers. So therefore, 1 out of, in how many different ways to write the ticket? Okay? So that is, you choose 6 out of 53 without ordering. You can say just 30 and then, whoops, I like 6, and then go on, 1, okay, and then 39, and then 56 like that, okay, oh, choose one more number, so let's say 48, like this. Oh, 56, I'm sorry, it's not available, so let's say 53, like that, okay, the order doesn't matter. So that is a combination, that is 53, choose 6. So calculate it. So 53, choose 6. Do you know what that is? That is 2, 2, 9, 5, 7, 4, 8, 0. 1, one out of this many. So how many tickets? So I'm going to put some commas to give you good perspective over here. Comma here, comma here. Oops. 22,957,480 tickets are possible. Okay? And you make just one. Only one will win. So roughly I could say this way. 1 out of 23 million. Your guess is that good? Okay, if you win the lottery, that means yes, this tough. 1 out of 23 million possibilities, and then you just make the one choice. Okay, make one good choice. All right. Earlier I said it doesn't matter how many people buy the ticket. That one can be applied to like what do you call it, door raffles. Okay, so you go to a conference and they said, okay, you are going to get a ticket at the door, and we are going to call just one winner that give you good present or something, prize. In that case, how many people are in the room, it matters, correct? Okay? Nothing else. How many people are in the room, or how many tickets were given. So if there's 100 people were in the room, so that means 1 out of 100. But in this case, it doesn't matter. 30 million people, even 50 million bought a ticket, but if nobody chooses this winning combination, there will be no winner, correct? So this one has to be number of people who bought the ticket is irrelevant. When you talk about how much money you will win, even if you hit the jackpot, sometimes there are multiple winners. In that case, yes, it matters. But when you talk about this kind of probability, only one that matters is how many different tickets can you make. That's all that matters. Okay? All right? So we finished, the lecture 18, the conditional probability. That one I'm not going to do it. Okay? I'm not going to do it, and then skip to lecture 19. So in terms of probability, today is the last day, or last lecture, okay, for probability. From next time, all about money, the mathematics of finance and the interest. Yeah, you hear every day that the stock market is not doing well, and the president and the Congress, they are thinking about some stimulus package, and they all talk about money, after you talk about the coronavirus, okay? Well, this part you are going to use calculator. Without calculator, over here, at least some part that we were able to do by hand. From lecture 19, no way. I cannot do it. Probably you cannot do it, okay? Well, so I want you to have a calculator next to you every time. Do not just look at me, oh, Dr. Han gives me an answer. Don't do that, because when you do your own homework and the quizzes, it's going to be a very, very important issue over here.